Yeah, nice.
Ladies and gentlemen, good afternoon. We will start this session on reservoirs, and the exact theme will be the reservoir characterization, monitoring, and management. I am Mohamed Hedi Nagra, professor at the Faculty of Science of Tunis Al Manar, and I will be really happy to chair this session. So first of all, since the first lecture is cancelled, Mrs. Meshket Yahyawi from ETAP, geologist at ETAP, in the sedimentology and pedrophysics lab, will start this session by presenting the presentation entitled Fracture Study of El Gari Reservoir, Ashtart Oil Field, offshore Tunisia. Meshket.
Thank you very much for being here. I hope you have enjoyed your lunch, everyone. So this is Meshket Yahyawi, a geologist at ETAP, Sedimentology and Petrophysics Laboratory. And I'm going to talk to you about the fracture study of El Gari Reservoir Ashtart Oil Field, a work that was elaborated with Mr. Mohamed Sousi and Mr. Sofian Shaib. So Ashtart, the name, it symbolizes fertility, and Ashtart oil field has always been a fertile oil field, and it was one of the most important discoveries in the oil and gas industry in Tunisia, and it still is. So the question that we will try to answer today is whether the fractures on El Gari Reservoir Ashtart oil field would enhance this this fertile character of Ashtart oil field or not. So we will discover this together in a while. So to start with, I'm going to present the Ashtart oil field and El Gari Reservoir, of course. And then I'm going to talk about the fracture attributes that were collected from the cores that were studied, because this work was based basically on the study of cores and then comparing the attributes that were collected from the cores with the well logs that we will see in a while. And then with all the elements that have been collected, we will try to identify what type this reservoir is according to the Nelson classification. And in conclusion, we will try to answer the question, do the fracture within El Gari Reservoir enhance the reservoir potential or not? So, Ashtart oil field was discovered in 1971, a little bit of history, very important. It started operating in 1974 on a reservoir that has become since a target that a very important target in the oil and gas industry in Tunisia, and it's El Garia reservoir that is 7 meters thick and that produces 895 cubic meter per day, which is equal to 5,629 barrels per day in 2013. El Garia reservoir is a Eocene reservoir, to be exact. It's a Parisian. It's limited on top by Shirahil and on the bottom by Shwebin. It's a shallow marine nummulitic build-up limestone, backstone to grainstone, that belongs to the depositional environment of a middle rump. And its porosity is essentially interparticular and intraparticular with intense dissolution. So its porosity is essentially due to, it's based on the matrix. It has a high porosity, around 35%, and a fair to good permeability, and its facies is built on a succession of age-equivalent carbonates and evaporites, outlining extensive carbonate rump during epresion. About the geological structural setting, it's a structural high on succession of northwest-southeast horsts and grabens, normal faults of course, and the faulting took place in multiple extensional phases with reactivation of pre-existing structures, and we can see here the faults on 2 cross sections, and the general structural setting of Ashtart oil field, which is in the Gulf of Gabes. This extensional phase was temporarily interrupted by a compressive phase oriented northwest-southeast that gave birth to the uplift and erosion that gave this particular structure of the Ashtart oil field with those horsts and grabens that will later influence the structure and the depositional pattern of El Garia reservoir. So the wells that have been worked on are 5 wells that were reoriented. It's a total of 447 meters of cores that were examined. Presence of fractures was noted that could be seen on cores or borehole images from FMS, FMI measurements. Well, this is the top El Garia and bottom El Garia in every well. And as I said, the total core length studied was 447. Now we're going to see the classes of fractures that were examined. There were mainly 2 classes of fractures based on mechanical origin. First of all, we have the joint here that is filled with a cement that, of course, is not related to the drilling fluid, and it's a vein, and the slickened sides of a fault. So this is basically the 2 classes of fractures that were identified. And in terms of morphology, there are 2 types of small-scale natural fractures. The first type is open or cemented planar fractures. And as we can see, well, here it's not a completely open fracture, but it was partly open and then the rest of it was induced. But with this fracture, we can see the bitumen impregnation within the fracture that is a very good evidence that, well, in some point, the fractures can communicate. The second type of small-scale natural fracture is the tension gashes that are associated to the stylolites. We can find them associated to stylolites or just enclosed within the cores. Now, in terms of orientation, and now we will see where the problematic with the the fracturing in Angara Reservoir will start. We can see that the two major sets of fractures are north 135 to 140, that goes to 150, 160, 170. And it's the orientation of majority of faults. And fractures here are predominantly subvertical, dipping uniformly either toward northeast or southwest, which is linked to dip direction or nearby faults. But here, the fact that these fractures are subvertical, and with this dominance, it will give us an insignificant contribution to the fluid flow expected toward northeast, southwest. In terms of intensity now, these are the well logs that were worked on from the 5 wells studied. So 151 fractures were recognized on 447 meters of examined reservoir rock, which gives an average of fracture intensity of 0.33 fracs per meter and an average fracture spacing of 2.96. We can see here in red, the red is the fractured intervals, and the blue is the stylolithized interval. The fracture swarms are located here in intervals with very low matrix porosity, and we can see that on basically, not all the intervals, but basically the sonic logs that are associated with every well log in here. And this leads us to the first interpretation that the more the rock is compact, the more it would have more fractures than porous rock. And here, as we can see, also the caliper, its variation, there's a huge washout that could be a reliable indicator that there is intense fracturing here, especially when we attribute the depth of the identified cores to the well logs that we have here. And with attributing the same depths with the depths that the faults in Ashtart oil field reach, we can say also that the fracture intensity seems to increase with fault proximity. Now, we will deal with the stylolites, which is a dilemma here because they have two different effects on the occurrence of fractures in this reservoir. Well, as we said, the reduced porosity facilitates fracturing. So, with the occurrence of the stylolites, the porosity will reduce because the carbonate that gets dissoluted from the rock will seal the porosity present primarily, and it will give a less porous rock, so a rock susceptible to have more fractures. But in the same time, stylolites also can be a good place to precipitate some impermeable and insoluble materials that will be dangerous for the permeability of the reservoir. So the stylolite can help to make fractures happen within the reservoir. Also, it can deteriorate the permeability. So its influence here, it's problematic, as we can say. Now, as we said, fracture intensity seems to increase with fault proximity. And here, as we can see, the position of the wells studied on the map, some of the wells are intersected by faults, some of them not. But when we see the well B and the well C, they are the most fractured. And there's a major fault striking the position of the wells here, which lead us to say that the high fracture intensity is associated with major fault network, which gave us the well B, well C, and well E that are associated with major faults. And the more we are far from the fault, the more the occurrence of the fractures decreases, which is the case in well D, no well or fault intersection, and well A that is in between, because there's a possible fault ramification affecting the well in the bottom. Now, to talk about the most delicate attributes that we can try to study on a core, because when we study a core, we have just a limited part of the reservoir, so it's really difficult to try to predict the length or the aperture of the fracture. But from what we have, the rate of open fractures can reach 100% in some depths, like in here, in the depth 3,000 in most of wells, and 2,800 in most of wells, which corresponds to the occurrence of the major faults, the depth in which the major faults occur. So, to sum up, fractures are predominantly open and oriented, corresponding to faults in a general northwest-southeast direction. Two major sets of fractures were identified, north 135, north 140, to north 150, and north 160 to north 170. As we said, the major set of open fracture that could show influences on the flow is the one associated with the major fault network pattern with one main direction, that is north 140. As we have seen, the highest rate of fractures is at 2,800, which belongs to well B and well C, the most fractured wells, and at 3,650 meters in well E. The fracture intensity is high in the low porosity rock intervals. It is also largely affected by the degree of compaction and stylolithization. And the most important information, that when we find a great intensity of fractures within an interval, yes, we can be happy and enjoy the news, but it's not always a case that is really enjoyable, because these two parts of, these two or three or more intensely fractured parts must communicate in order to enhance the reservoir potential of a reservoir. Because when they are isolated, those very fractured parts, we will be dealing here with something like this. The Gary couples in connected highways. We have here, for example, nice multi-lane highway that does not have traffic because it doesn't connect to anything. We have very nicely established roads that serve to nothing. That's why we need to find those even very tiny fractures that must connect two parts of a reservoir that are heavily fractured. To sum up with this diagram from the work of Nilsson, 2001, I classified El Gari Reservoir in a type 3 reservoir because we have a matrix property domination, of course. It's very well known about El Gari Reservoir. Its matrix is homogeneous. It's excellent. The reservoir is excellent in terms of matrix, but it's so heterogeneous in terms of fracturing. We have predominantly moderate fracturing, which leads us to say that we are not dealing with a classic fractured reservoir. The well C, of course, is exceptionally large, has exceptionally large number of open fractures. The fractures constitute high permeability in places, which makes the reservoir really heterogeneous. These are the references of the work, and thank you very much for your attention.
Thank you, Meshkat, for this good presentation, also in time. So we have more or less 5 minutes to ask questions. So, if you have, please.
This is Bilal Tatak, reservoir engineer from Shell. Thank you so much. It was quite clear presentation. So a couple of questions for you. For this faults and fractured network, how this network is connecting the hydrocarbon column to the aquifer? This is question number one. My question number two is, in case that your network is not connected, how this what proposals you are given to reservoir engineers, to the subsurface team to enhance recovery from these regions? Yeah, thank you.
Thank you very much for your question. Well, in case we have a fractured reservoir in two parts that are not connected, maybe the enhancement of the quality of this connection in the reservoir must be required. That must be, we need to have a backup from the well test data, production data, that we need to incorporate with this core lab analysis of the cores that we have in order to determine in which layers the fractures.
Would you recommend frac jobs for some of these wells?
Well, if I will deal with such case, and if the team would agree on that, yeah, but I can't take the decision on my own.
Yeah, but okay. For my question number one, is this network of fault is connecting the aquifer to the hydrocarbon column?
Well, you know, the fractures within El Garia Reservoir are still a topic of research. El Garia, it are asked now and keep to be asked if of whether the fractures might enhance the production of El Garia Reservoir. So maybe in the future you will have more precise answers.
Thank you so much.
The intersections between them and the interconnectivity of them. So have you done anything to estimate fracture lengths?